All right, onward in our proof to produce an more rigorous version of complete proof of Arnold conjecture that does not use special nice geometric perturbations for moduli spaces. So, well, recap, and also, well, I forgot one obvious thing to write down. So we're going to want to make all these maps from certain moduli spaces, and then we need to prove some algebraic statements about them. Right? And when I wrote down the PSS moduli spaces, I parameterized them by a complex plane. Then there was an evaluation at 0. Condition that, ties in the Morse trajectory. And then I always just set energy finite, which then implies that, down the sort of cylindrical end, I'm actually converging to the periodic orbit of my non-degenerate Hamiltonian. I did fix it with gamma, so really I should add that the limit is gamma. So, and then I color-coded this a little because I want to think of this a little bit as a fiber product of these two separate things. Right? So I want to think of it as a just moduli space of perturbed holomorphic curves with one marked point. So there's an evaluation map here to my ambient manifold. And I already made evaluation maps from the Morse moduli space. In this case, this simply is the evaluation to the unstable manifold. But the nice thing was that I extended those evaluation maps to the compactification. So with pictorially, what this means is I've written my PSS moduli space as the fiber product of something that I would like to call M plus, because it has a positive end. That just knows gamma. And then I have a fiber product over M with the half-infinite Morse moduli space of things from P to M. And really I should switch those two. Let me not do that. Right, so that's the Morse moduli space, and this is the holomorphic curve. And right, there's the area where my cutoff function is non-zero. That gives me this perturbation. So I sort of try to pictorially show you where the perturbation is supported. So key here is that I've just wrote this as a fiber product, which we're going to make some use of. And now, the SSP moduli space works exactly the same way, right? Except we have slightly different coordinates, slightly different cutoff function, and I'm going to call that M minus because there's sort of an incoming end at, right, the cylinder R goes to minus infinity. That's where my periodic orbit sits. And then the stable manifold, I want to replace that stable manifold by these half-infinite Morse trajectories, because eventually I'm going to want to compactify that in a way that I sort of mumbled about last week. I don't want to compactify it within M. I want to compactify it within the Morse trajectories, which is sort of more data. Right. So that's PSS and SSP, and then I want to compose them and homotope that to something that hopefully is going to be an isomorphism or Morse homology, and so that is going to be very similar fiber product, except now, right, I have this middle piece of holomorphic curves where, well, there's always two marked points, but well, for R finite, just the PDE changes, and then at R equal to infinity, I'm actually changing the domain. So there's a whole bunch of equations on CP1, right? And in the limit, I'm going to sort of break this into a PSS and an SSP curve. So, but those two still have their marked points here. So there's always two marked points on it. So I can think of this as a union of these moduli spaces, and then I have two evaluation maps, so I can have two fiber products with my two Morse moduli spaces. That should be a P minus here. So this union here by itself now is not quite connected, right? So I need to put some kind of Gromov topology that connects this to the nearby ones, right? But some kind of gluing situation. That's so. Describe this now as a fiber product. Right, and you can already, so there's sort of two neat things that are going to happen. So as you set R equal to infinity, right? Really, this bit here is a product. Right? So if you write this product in here, then you actually see one fiber product times another fiber product, right? And those are your PSS times SSP. That's the one boundary here, and at R equal to 0, we just call that the other boundary. So same fiber product, except now I've fixed R equal to 0, and my decision is that at R equal to 0, I've just completely killed that perturbation. So that's the unperturbed holomorphic curve here. And I should maybe let me put a twiddle over these. So twiddle is sort of often used as a notation for things where we don't quotient out by isomorphisms. And nowhere in these moduli spaces have I quotient out by anything. Except in my Morse moduli spaces, maybe if when I've broken ones there, like shifted by R in those. And so what we did last week is we assumed that these moduli spaces by themselves were somehow essentially compact, or just had sort of exactly the kind of boundaries and ends that we wanted. No sphere bubbling ever happened, so everything was nice. So now let's see what real life looks like. So, right, first kind of pictorial horror scenarios. Right? So, what can happen if you have a sequence of solutions here? So, one thing that we know with holomorphic curves can happen is sphere bubbling. So this might not converge on the entire plane C, but there might be some places where energy concentrates. So it's by itself, it's just going to sort of C infinity log converge to something on the complement of finitely many points. So this is your C infinity log limit. And then at those finitely many points, energy concentrates, and we spent some time last year sort of trying to explain how we can see geometrically what happens there. So you see a whole bunch of spheres, could be whole trees, could just be a single one. And each one of these you get by rescaling these guys somehow locally near those points. So these are all somehow limits of some sequence of U nu composed with some rescaling psi nu on some large disks of, say, radius R nu, and R nu goes to infinity. So in the limit you have a whole complex plane, and then you can fit in infinity and remove the singularity there. So that's how we find each one of these spheres. And the game is that I want to capture the entire energy. Right? So once I can't find any more energy here, I ask myself, well, what else might have happened? Right? And because I have a non-compact domain, energy could have flown out there. So something else that could have happened is that when I push everything into, so when I sort of rescale myself into domains that go down the cylinder, I might get a new limit here. So these things here are limits of, there's a theta that goes, oh goodness, from C to the cylinder, so I should write U nu composed with theta inverse, and then I shift with some S I nu plus dot, comma, dot, and the S. So the first one I get from an S1 nu going to infinity, and then the second one I would have to shift even bigger, so S2 has to go to infinity faster than S1. And then again, these might just be C infinity log convergences, so you might get even more gradient concentrating, so there might be bubble trees on any one of those. The reason I'm trying to say sort of somewhat specific how these limits occur is that I want us to recognize that there are choices involved. So for U infinity, there's really no choice involved. You just keep track of, you might add marked points eventually where the energy concentrated, but the sequence knows that. So there's no choice there. In finding these sphere bubbles, there is a choice of, on what kind of disks do I rescale and how do I rescale. And, there's different choices that will all give me somehow convergent sequences. So eventually we're going to want to quotient out by the ambiguity in those choices. Similarly here, in order to capture all the energy, I know how, my sequence is going to know how many pieces I'm going to need to get and essentially how fast these shifts have to go to infinity. But I could just add a constant to every one of these and I would still converge to the same thing, just shifted. Right? So those shifts are things that I'm also going to want to quotient out by eventually. Which, to a lot of you, if you've seen these compactifications, might look completely familiar. The nice thing is that there's a good analytic reason why in some pieces we quotient out and in others we don't. It's just, by the ambiguity of how you find the limits. All right. And, right, one thing I haven't talked about yet is what happens to this mark point. That mark point also, if you're now somehow not really looking at the analysis, you ask yourself, well, why does that mark point not go to one of these? Well, it's in a domain where the perturbation is 0. And so it's very firmly in that domain where U nu converges to this U infinity, C infinity log. It's not, that point is not running out to infinity on C. Right? So it's certainly going to be somewhere here. However, nobody says that energy can't concentrate at 0. Right? And if you do that, then you rescale the thing and that marked point might go off on some sphere. So, mark point can end up on any one sphere, and then nobody says that you're always going to lie in the sort of actual unstable manifold. You might, this point in a limit might lie on, the closure of the unstable manifold. And so here I now have a choice of putting the closure in M of the unstable manifold, or taking some other compactification of that. And I took the compactification where I don't just want to remember this point, I actually want to remember the image of the trajectory. So I want to see the broken Morse trajectory. Right. Yeah, and the other thing is that here these spheres are attached in places where there was no perturbation. This might be somewhere near a perturbation. These are certainly spheres that happened when there was perturbation. But we're rescaling so drastically here that we're killing all perturbations. Right, so all of these here are unperturbed holomorphic things. All right, so horror scenarios just for the PSS. However, so just to sort of get ourselves a little unfreaked out, let me just sort of give you the mantra. We expect sphere bubbles to be interior points, or maybe codimension 2. So certainly not expecting somehow boundary from sphere bubbles. Breaking is going to give us boundary, but that's sort of nicely linearly organized here. And then, our Morse moduli spaces have boundary. But those I've already given smooth manifold with boundary and corner structure. So, there's something wonky happening near the spheres, which we need to deal with. Right, there's also symmetries that might, that the spheres are exactly the places where you might quotient by something and you actually have fixed points of finite stabilizer subgroups. So they do create some issues, but somehow it's not boundary issues. So. Right. Once you've seen this, you can do all the other moduli spaces. In particular, you can just flip all these pictures and draw what happens with SSP. So a little bit more interesting maybe is what happens when you look at this moduli space for the homotopy. Because now we kind of have our data really is a pair of some number R nu and U nu, which is a solution for that specific perturbation. And so as nu goes to infinity, I can first just see what happens with R nu. So there's one case, again, I should find this convergent subsequence, but maybe I can find a convergent subsequence where the R's go to something finite. So then I'm certainly expecting the U nus, which are all defined on CP1 now, to again converge C infinity log to something. Right? So there's a U infinity, and again, gradient can concentrate. Gradient can blow up, energy can concentrate. That gives you all these sphere bubbles here. Morse trajectories can break. Mark points can lie on the main component or can lie on the sphere. What doesn't happen here is that energy goes off to infinity someplace because my domain does not have any non-compact ends. So no breaking here. Which is nice because that means all the expected boundary strata just come from the Morse moduli spaces. Well, and then there's the case where R goes to infinity. Which is, there's sort of now two sources of breaking, right? We already saw a breaking here where energy went off into a non-compact end. And here we're kind of forcing breaking by somehow making a strange perturbation and actually degenerating our domain in some sense. So there's a bit of forced breaking involved. And the thing with forced breaking is once you force stuff to break, you can't control whether it just breaks once or several times. Because what you do is you make, a part in the middle that, is essentially becoming a cylinder on which you have this R invariant equation. And, within that cylinder, you could have blobs of energy that run apart. And so then, when you're trying to really, describe your limit, you might see broken Floer trajectories. So, this I should get to again a little bit. This, there's some subtleties involved here in understanding how exactly this breaks into several pieces. That's sort of really, that's best understood as part of symplectic field theory compactness, where, the buzzword is these are buildings, and you can't quite control the number of buildings the number of levels in a building once you let a building break into several levels. But what you can control is, there's always a finite part of, there's say a disk of radius, 25 over here, on which the equation always stays the same. And it's just, outside of that disk that, the equation becomes longer and longer equal to this, just sort of Floer trajectory. So, or you could think of this as a half-infinite cylinder here, another half-infinite cylinder here, and then a finite length cylinder in the middle on which you have the standard Floer trajectory equation. And so these two half-infinite cylinders, on those you'll have C infinity log convergence to these two pieces. And you have that on, disks of every size, because that Floer trajectory bit goes to infinity. So you're actually going to get an infinite, so you're going to get to C here, there also. But then something extra, some energy might actually also sort of concentrate in the middle bit. And so those are sort of extra trajectories that we're going to see here. And again, the blue stuff is going to be strictly parameterized, and on the gray things, you'll have some choice of how you converge there, depending on what shifts you use to get there. And again, sphere bubbling can happen pretty much anywhere. So, I've killed there. Right, so that's right. Sphere bubbling can happen anywhere, and again, the marked points will stay. You've forced them on those two bits, so they will be on those two parameterized ends. They could just bubble off with the spheres. And if I now take so the only other map in the picture is the one when I look at the R equal to 0 part of this. And that's also a little dicey, right? So if I just forget R, whatever R might do, I get to this kind of picture. I don't have this perturbation sitting here, but there is a difference. There's this blue bit which is parameterized, right? And all the sphere bubbles are unparameterized because I need to forget how I rescaled to get them. So again, this will go C infinity log to some U infinity, and again have a whole bunch of spheres comes from parameterizations. Right. So that was a qualitative description. Right. If we want to do rigorous math with that, we need. I feel one needs to put it in formulas. So let me try to do that. So this is where things get atrocious and papers get long and unreadable. And really you're tempted to just sort of write the first couple of pieces that are, don't look so atrocious. But I think then it's kind of easy to forget somehow subtle things that might happen once you have 25 pieces. And usually the subtle things don't happen at 25, but at 3. But we're often, tempted to just write down 2 pieces. So I'm supposed to somehow encode this here, right? So, and here is, right, so here's the, I'm trying to compactify this moduli space where I don't insist that that's a dense subset. So, right, so these are my holomorphic curves and there's the Morse space. So, this looks like a fairly safe idea here. I'm just going to take the compactified Morse space. So I have the broken guys. That has an evaluation map to M. And so now I need to encode the whole bubble and breaking tree. That should also have some evaluation map. So, and in fact, I know that there is a first piece here that will have that evaluation map. I'm going to call this M plus of gamma, which might not, so the outgoing periodic orbit might not be gamma anymore, that would be gamma 2 in this case. And so since 2 is not general enough, I'd better take union overall K, which would be, so there will be an M plus gamma U. Which way do I want to do that? Oh well, K. And I would like to call that compactified, but I don't want to add all of these broken pieces into it. I just want this piece that's parameterized together with spheres. So I'm going to sort of start using the notation sphere compactified. So it's the parameterized guy where I'm taking care of gradient blowups, so I'm adding spheres, but I'm not taking care of energy running off to infinity. So that's this guy. And that again was going to have 1 mark point, so this will have an evaluation map to M. Once I've written that out properly, so I need to actually define what that is. And then I want to introduce these actual Floer trajectory spaces. So, gamma K. So I can flow from gamma K, there's a Floer trajectory, gamma K minus 1, and so on up to something that goes from gamma 1 to my original gamma. Right, so now I forgot that there's a choice of the gammas, so I need to keep track of the fact that I can choose all these gamma i's at which I'm breaking. And what else? I've forgotten sphere bubbles on each one of these, so I'm going to need to sort of sphere compactify all my fluid trajectory spaces. Yeah, atrocious, not terrible, right? Big, just Cartesian product with, you know, one fiber product here. So, and to be very anally precise, let me try and actually write down the definition of all these new modular spaces, right? So, with the fluid trajectories, right, these are defined on cylinders. Just the fluid trajectory is now R invariant, which also means, right, I'm going to quotient by that R. That was exactly the argument that I didn't quite know how I converged there. There were some choices of shifts. Finite energy means I converge to some periodic orbits. I'm going to fix the ones when I write gamma minus and gamma plus. That's that. Before I sphere compactified, and now I need to say what I mean by sphere compactification. So before I can say that, I need to say what sphere bubble trees by themselves are. So, and I'm going to try and say what a simple holomorphic sphere with k-marked points is. Right? So that's just going to be a map from P1, which is unperturbed holomorphic, and, well, in this whole story I've just fixed a single J on M. Yeah, I'm not going to fuss with that. So that means here I have full symmetry of the entire reparametrization group, which I do need to quotient out by, because I didn't know how I converged to that bubble. I do know that I have finite energy. I don't know for sure that, say, a sphere like this here is actually non-constant. It could come from sort of two non-constant spheres kind of wanting to bubble off and wanting to bubble off at the same point. So this guy here could be actually constant. But it's constant and it has 3 marked points, which makes it stable. So we like that. So here I'm going to want to say at least either I have 3 marked points or more, which means it's one of those ghost bubbles where that comes from, you know, marked points colliding, or it has otherwise a good reason to exist, namely energy is positive, and I needed to capture that. So that's my stability here. And right, stability is reflected in my decision that I wanted the, right, so far this had nothing to do with the marked points. Well, I said there's 3 marked points. I would like my marked points to all lie on the domain, and this is sort of the master diagonal. I want no 2 of them to be the same. If I did allow 2 of them to be the same, then I wouldn't need the stability condition of, you know, having, well, then I wouldn't need to allow ghost spheres. Right? So allowing U equal to constant is what allows me to make these disjoint. Phew. Good. So right now here, well, the automorphism group, you know, moves both the map and the marked points in such a way that I have a reasonable evaluation map from this at all my k marked points. Good. So now I have made sense of sort of the picture of a single sphere, for example, this yellow one here with its marked points. And so now the next thing that I want to make sense of is an entire sphere tree, like this whole thing that sits between the main PSS part and the extra mark point for the Morse trajectory. Or this little sphere tree, Mickey Mouse, that sits on my Flood trajectory. So the common feature, ooh, goodness, of not quite all of them is that they have exactly one important marked point left, right? So this here has just that one marked point where it's coupled to the Morse trajectory. This has one important marked point where it's coupled to the PSS. These all have one important marked point, except that one's also going to have that extra Morse marked point. So I might not be completely anally complete here. So let me try to write down the guy with one important mark point. Right? So now I need to take somehow a union of all possible trees. And then each of these trees will have a root exactly where the important mark point sits. So it's going to be one important mark point and some extra k's. And alpha 0 is going to be my root of my tree. And then for all other vertices of my tree, I'm just going to have some number of mark points on my sphere. So far so good. That's all the spheres, except they're sort of not connected yet. So I need to somehow encode that these nodal points here actually match up. But I have all my nice evaluation maps, so from this whole thing here, there's some massive evaluation map to some large M. And I'm actually going to think of this as products of M, because for every edge, oh wait, not 2E, just 1. And so the thing I also haven't told you is that every edge right between two vertices should come exactly with one marked point on each of the vertices. So that means that every edge gives you 2 marked points somewhere here. So from all of these things together, I should get one big evaluation map to points for each end of the vertices, so for each end of the edges. And what I want to do is I want to take the fiber product over the diagonal for each of these edges, because I want the 2 marked points to evaluate to the same thing. So for each edge, I have one diagonal there. Right. Good. Which leaves me with exactly one more evaluation map at this one extra marked point here. And that's my one evaluation map from this here. Well, as this is written, it's not quite a compact space because there's infinitely many tree types. But when now Gromov compactness tells me that if I take somehow the part of this moduli space that's finite, that's up to fixed energy, then that's going to be compact and has a nice evaluation map. Right. Okay. And right. At some point, I fear later on, I might need this with 2 marked points. Question.
Is there a difference difference between two ghost bubbles with 3 points touching each other and one ghost bubble with 4 points?
Yes.
Are we supposed to exclude the adjacent ghost bubbles?
No. Well, so let's see. Let's see what's happening here. 1, 2, 3, and then 1, 2, 3. So this is the limit of a ghost bubble with 4 mark points as 2 of them run together.
So there's still a meaning even for ghost bubbles of mark points running together?
Yes. Yeah. Yeah. I mean that's the Deligne-Mumford space, right? So this is a space of constant holomorphic maps with 4 mark points. That is not just a point, that actually has some modulus, and in this case that is, this moduli space by itself is the sphere, right? Because I can fix 3 of them and then the 4th one can be wherever. And so, except I've fixed the 4th one to be not equal to any of the 3, so it's sort of the 3-punctured sphere, and it gets compactified by these bubble trees. So, right. So if I read this here with u equal to constant, here, right? I don't allow my 4 mark points to coincide ever.
Yeah.
Right? And so I need to add chains of ghost trees, when mark points collide.
I just don't remember.
Yeah.
So when you run a sequence of actual holomorphic maps, you can tell what the ghost bubbles are.
Yes.
Okay.
Yeah. You just run your soft rescaling, right? And right. Exactly. Okay. Let me not try to go into that proof.
That's fine.
Yes.
But the statement is yes, you can detect what the modulus of your ghost bubbles
right.
are.
Yes. It will happen. Eventually, every one of these mark points is some place where energy concentrates, and we keep those up. And then there's the extra decision of keeping them apart. Right. So yeah. Right, that's in terms of detection, and just in terms of making sense of these moduli spaces as spaces. You could fix the energy. I mean, I could take this entire thing here and ask for energy equal to 0, right? Then this then all these k's have to be at least 3, because otherwise this is not admissible, right? But I could have some massive tree here, where all the evaluation maps will all go to the same point because my maps is constant. Well, at each one of them it's constant, and then this big fiber product makes sure that every one of the components actually maps to the same place.
Eventually, you're going to have a non-constant thing at each of these leaves. So.
Right. Yeah. Leaves. Right. Leaves in my tree eventually will be.
Just by the fact that they're stable.
Right. Yes. Right. Oh, yes. Yeah. Right. So if I only have one extra mark point. Yes. Exactly. Yeah. Exactly. Right. So. Good. Yes. Good observation. So. Every tree will have some number of leaves here, and leaves are not allowed to be ghost bubbles because they only have 1 mark point. So if I wanted this entire thing to be constant, I would need at least 3 mark points on it, which then would not allow me to bubble, because every time I take these things apart, I need more leaves. So if I increase the number of mark points here, I can get more components that are constant. Phew. Right, so those are just the sphere bubble trees. Right, so this explains what one of these is, and now I want to say what this whole sphere compactified off something is. And I want to do this, in one go, for this bit and also for like a fluid trajectory. So that's why there's lots of dots here, whatever the data is. I would like to say that how do I sphere compactify? Well, I ask myself at how many points was there energy concentration? That's 0 if I'm lucky, or more than that. And then for every n, I need now sort of the original moduli space but I need some extra points on the domain, so I need to keep track of the bubbling points on my domain. So these will be, in this moduli space the domain of U could change, so let me say these are marked points on the domain of U. And those are simply pairs. Right. And then from this here I have a nice evaluation map to M to the N, and I can take the fiber product over that with more sphere trees for each one of them. Right. M bar 1. N of these, each one has one evaluation map, so I can get myself here. Field. Right. Of course, I cheated a little again, right? Because in some cases I might have to write equivalence class of U. Because, for example, my fluid trajectories are quotiented by R. And then really what I should do here is not take the equivalence class of U and some separate marked points. I should somehow take the larger equivalence class of U, maybe in M twiddle, before I've quotiented and marked points, and then quotient by something like R. Yes. Yeah.
So the tree need not be stable.
No.
So then how?
Every non-stable vertex will have to come with a non-constant holomorphic curve.
So where does this constant spheres with k bigger than
Yeah.
in this description? So
they can appear in here. That's
So only at the base, only at the first.
No, they can be anywhere within the tree, right? So let's see. So if my tree, okay, goodness, let's see. I have a root. I mean, my root might have valence 25 or whatever, but every single next vertex might also have high valence, right? And then I might have. So if that's my tree, right, then let's see. Things that could be ghost bubbles, let me just mark the things that are not constant, right? Everything that has valence 1 or 2 needs to be non-constant. But this is let me even add one more. So there could be another vertex in between here. This looked as if there was sort of a connected subtree of ghost bubbles. So this could be a ghost, and then there could be some ghost bubbles there, you know. But I could have, you know, other places.
So do you mean like if K alpha is less than 3, then it cannot be constant?
Right. Yes. Right. So all the leaves here have to be non-constant, and each one that has, you know, 3 or more has a choice of either being constant or being non-constant. So, yeah. Crazy stuff. This is I think there's a nice description in McDuff-Solomon for, you know, really how you really see the convergence to a tree for spheres. Good. Right. So all this work just to say what the limit for PSS was. Well, the good news is that SSP works exactly the same way. So let's see here. Right. A little more cleanly written. Right. This was PSS, simple fiber product, and I get it compactified by allowing myself any number of breakings, and right, so compactifying the Morse moduli space, and I sphere compactify every single one of the Morse trajectories and the main PSS there. Okay. So now again, you flip the whole picture, you get SSP, and H should not be that much harder. Do exactly somehow the same starting point. We write this as a fiber product that we had for the homotopy, and then what? So for one thing, certainly that's these guys here. If I'm not breaking, then all that can happen is I need to sphere compactify my main component. Oops. And then there I'm cheating because now I should have 2 mark points on this. Right? So I haven't quite strictly speaking defined this, but I should, you know, keep track of 2 mark points that are somewhere. And I have evaluation maps, and I'm just going to replace them, Morse moduli spaces, by their compactifications also. However, I might also break, right? So I should add that. So, and now I can break any number of times at any possible periodic orbits, but always there will be first a Morse trajectory, then there will be one of the PSS guys, so I can take an M plus S2 compactified, which will end at some gamma 1 in this case. Then in the middle I'm going to have some Morse trajectories, and well, more Morse trajectories. I end with some sphere compactified gamma k of the SSP, so that's a minus. Right, I should sphere compactify my flow trajectories, and this last guy will have some marked point either on the main component or a sphere, and I have a fiber product to M. Right, the Morse trajectory space. that is all fine for us, and I don't think we need the following worry, but I'd like to add that a little for your entertainment, and also so if you actually sort of go a little bit beyond this at some point, you're aware of this little dicey question. I would really like to sort of think of this, right? H is supposed to be a cobordism between r equal to 0, which is part here, and some bit at r equal to infinity, which should be just the product of a PSS and an SSP. Right? And that's all not so bad. I can, I mean, here certainly it's clear where I would like to break this whole thing. Let's say this is SSP, this is PSS, that's SSP. Here I'm not so clear where I should be breaking this, which gets algebraically reflected in saying I don't know at which gamma L I should write this as the sort of part, the compactified, this is part of the compactified M plus of not M plus, sorry, this is the PSS guy, which comes from P minus and goes to gamma L then. Right, and then this other part here would be the SSP guy from gamma L to P plus. But when I have several breaking points here, I don't know which the gamma L is. And that is a case where I might want to sort of be a little bit more careful and sort of maybe mark 0 in my cylinder here. And then in the limit, I see where that marked circle sort of goes in my building. So that here it has only one choice of sitting in the middle here, but when there's all kinds of breaking, there's sort of energy not quite concentrating, but floating apart to the left and the right of this, and I just keep track of where that marker goes. That's going to be someplace.
This is as long as no energy accumulates at 0.
Well, right, and then if energy, so the marker could be at one of these infinities, which would be nice, but if the marker is here, then I think I just need to make a decision whether I want to think left veering or right veering. Right. So, there's a little bit of interesting combinatorics going on. In this case, it shouldn't bother us much because really we're thinking that breaking adds one codimension in the right to the sort of corner index, and so once you have an extra component in between here, you already have two breakings, so you're at a corner and not a boundary. Right? And so then it totally makes sense, because into a corner you want maybe this number of choices here is exactly the faces that come into that corner. Still, one shouldn't just write this, you actually need to write this as a long chain. You don't just want to write this as a union over these broken things into two big pieces. All right. So, and now, right, so looking at the r equal to 0 piece of this, at least we don't have the marker problem, but I decided to write out a little bit of the confusions that happen from where does the marked point really end up lying. Right, so that's right. So now I'm really just taking this whole thing, I'm taking the r equal to 0 piece. So it should just be, this fiber product of the compactified Morse spaces with this sphere compactified sphere space. But the funny thing is that there's one that's parametrized, right, and all the others are unparametrized. So if I try to write this out, it's not one of the it's not quite one of these sphere bubble trees, because here all of them I quotiented by the Möbius transformations. So if you try to write this out anally, right, you want this kind of tree, and you want two evaluation maps at those two marked points. So there's the first part where there's no bubbling, and my two marked points are simply at, my two evaluations are simply at 0 and at infinity. And then four different things can happen. I can have n bubble points, and like in this case, my marked points actually end up on bubbles. And then there's two of these compactified sphere bubble trees that actually have two marked points. Right? One I use for this big fiber product, and the other one I use for the evaluation maps. So, right, I'm missing the m to the, oh boy, right, m to the power n. Right, so this has n evaluations, and each of these has one evaluation to m, and then some extra evaluations that survive in my moduli space. And then the other things that can happen is that, right, one of the marked points stays on the main component, either the 0 or the infinity stays on the main component, or both of them stay on the main component, but I still have bubbles. So that would be the whole frustratingly long, well, not yet compact space, because it's just the disjoint union of fiber products of things. But at least in terms of point sets, I've now written down as sets what I think my compactified moduli spaces should be. So. And now I want to make it compact, so I got to put a Gromov topology on it. And that obviously will have something to do with step 2 of our big scheme, which was to just construct all these maps. So here is the classical construction. So this is sort of the in the geometric construction. We were working just with the uncompactified space, and it's part of index 0 when we had, nice energy functions on it, and I wrote this sort of weighted sum, and I think I already remarked that you could group this into pieces of, first index 0, and then also pieces of fixed energy, so that I can really just write Q to that energy, and really all that I need to worry about is somehow counting this moduli space of things with fixed index and energy. So, and this is the piece where that moduli space now might not be compact, so I need to replace this by its compactification. If I want to run some abstract nonsense to say what that count is. So let me first sort of reconstruct all of this makes sense. So we did talk a bit about Gromov topology in the gluing. And so that has a couple of nice properties. One is that I can define an index by summing the indices over all my components. And I want to define the index so that it's the expected dimension, which means on every component, when I take the Fredholm index of the linearized operator, I do want to subtract the dimension of the group that I'm quotienting out by. So that's sort of my index of all the pieces. And I do the same thing with the energy, that I can sum over all my pieces. And the Gromov topology is so that that's constant, or locally constant on this compactified space, right? Meaning as you glue things together, the index adds and the energy adds. Energy is going to add, sure. And that's where you need to, index adds if you make this adjustment by, subtracting the dimensions of the symmetry groups. And then, well, this is not consequence of Gromov topology, this is really Gromov compactness says if I take the part of fixed energy, or up to fixed energy, that's going to then be compact as, subset of this topological space. And so now it's compact and the energy is locally constant, which means it's going to have connected components where the energy is constant. And so if I fix the index now, then I can write this as a countable union of pieces with fixed index k and fixed energy, where the energy goes off to infinity. But each one of these pieces is compact. And so when I write EI here, I mean not energy less or equal to EI, I mean energy equal to EI. So it's really only, if this is going to be compact, it's really only finitely many energies that are going to be possible. Right, so there's something non-trivial that happened when I said locally constant in energy. It's because I've made sure to define my energies so that they were homotopy invariants. Well, that's actually a lie. Right here I wrote energy as integral d as u squared. Of course, if I glue things together, I change that a little bit. But there's my energy identity that rewrites this in terms of a symplectic area, or as difference of symplectic action functionals. So really, that's what I ought to do with my energy here, right? So for the spheres, for example, I shouldn't use this. I should use integral u star omega. And that will then make sure that we're really locally constant and hence have this nice decomposition. So now essentially I did that so I don't have to integrate Novikov field valued functions over a modular space. And so now here's the proof. Well, no. So step 2 asks me to construct these maps. I'm going to use exactly this equation, which means I need to define a rational number from somehow my moduli space. That rational number I would like to be somehow the pairing of its fundamental class with 1 in cohomology. So it claims that that's a well-defined rational number. Meaning, first of all, it is actually a rational number, and then that rational number should be independent of some kind of choices involved. So, except now I don't get to say, well, it's a zero manifold because J was regular. So, the general phrasing of abstract regularization proofs should be now that this compact piece of my moduli space should be a zero set of something, namely some kind of black box section of index 0. So this 0 here should be that index 0. And that's really the piece that we have to prove. Yeah, that's up high on our to-do list. And then the second thing that's high on our to-do list is to find a place where we can quote the abstract theory from. Right? We should not have to do that again. So abstract theory should say that if you give them a black box section with compact zero set and it has index 0, then it should have a regularization, which could be, one of two things usually, either check homology class in the actual modular space, or maybe a cobordism class of weighted branch zero manifolds, which you get from some kind of multi-perturbation. So, right, when I say equivalence class or cobordism class, that has something to do with the blue thing. Oh no, even more things. Let's forget about the blue thing for the moment. Let me assume that I've actually fixed sigma. Right? Even once I've fixed sigma, in our case, this is not going to be a section over a sort of manifold. It's going to be a section over something that has boundary and corners. And that then means that when I perturb in different ways, I might actually get different counts. I might shoot, solutions off the boundary or not. So, depending on what my boundary combinatorics is, I might get different weighted branch manifolds here. So there's some kind of problems, right? And the check homology class can also have some ambiguities. So if there was no boundary and corners, then even this choice here, the uniqueness would be cobordism. In general, it's going to be a little worse because your cobordisms could have extra boundary on the boundary of the ambient space from which you cut your moduli space out. And then there's the extra problem that this sigma might be a Kuronishi atlas, and in order to make that Kuronishi atlas, I've made choices. So the section by itself isn't unique. It's just unique up to black box cobordism, hopefully, something I should prove. And then black box cobordism should also give me somehow the same invariant here up to something. So we're going to need to say this carefully for different values of black box. So let's see. The easiest story, black box story, was Siebert's story, where sigma is simply a continuous section in a Banach orbit bundle, which locally looked like a Fredholm section and had something that he called Kuronishi structure. I'd rather called it a global stabilization. But really it's a continuous map between topological spaces here. And he gave that an Euler class. So if you're lucky, that's your regularized check homology class here. The problem is that there is no sense really in which I can give this base C0 manifold a good boundary and corner structure. You could talk about boundaries of topological manifolds, but a boundary looks the same as a corner. And so that becomes strange. So there's a reason that Siebert only claimed Gromov-Witten and not Arnold conjecture. It's because there's no good reason to talk, no good way of talking about boundary and corners of this topological Banach orbit fold B. So we're going to have all this breaking in the picture, so we really shouldn't be going in and trying to use Siebert. So the next candidate that I've already talked a bit about is the Kuranishi idea, right? Where black box now has the name, I guess, Kuranishi section, and it's a little bit of a lie now to be talking about one section, because really there are a lot of local sections and a lot of local charts, so that really the zero set you're getting from gluing all these zero sets together with some transition data. But that was somehow the realization of some category. So it's sort of a categorical, well, there's a section between categories and you're taking the zero set in the realization. But then we can make sense of this a little bit more, because these underlying U's here were pieces of smooth manifold, so these can have smooth structure, and they will have boundary and corner. Except Duse and I did not try to do that with boundaries and corners, so somebody need to go into Fukaya et al. To see how you deal with that. And what I'm going to promote next is the Hofer-Vysotsky-Zinder approach, in which I really think this sort of language fits best. In your dreams, this was the zero set of a Fredholm section of index 0, and Hofer-Vysotsky-Zinder are going to make your dreams come true at the expense of putting polyfold in front of every occurrence of Fredholm. So what then happens in terms of boundary and corners is that your base polyfold, which generalizes the notion of a Banach manifold or orbifold, this will have boundary and corners. But, once we know the value of black box, we can look up, statements that tell us you can count zeros of black box sections. And those certainly exist. Once we have that, and I'll try to decode that a little more, we get to the next points that where somehow we're going to need to talk about the section restricted to the boundary, and then the section restricted to the boundary should somehow give us our algebraic identities. This and also, that's right here. And the other algebraic identity, that there's a chain homotopy equivalence between this I and the composition of SSP and PSS. So, somehow from the boundary, we're going to need to get those identities, which is a little bit pesky to say. And finally, we're going to need to actually calculate I, which is going to be nice and simply not much different. Right, so let me actually do that quickly here. Right, so that's going to define this, and it's going to tell me that really to understand whether this is an isomorphism, I just need to understand whether I is an isomorphism on Morse homology. And the silly thing that happens here is that you simply observe that your solution space for negative energy is the empty set, and for zero energy simply is the constants. This is your unperturbed solution space. The empty set is regular, right? It's cut out transversely, You can also convince yourself that the constant solutions are cut out transversely. So these are nice and regular. And then you would like some part of your sort of big perturbation or regularization theory to just say that once you have regularity on a connected component, you don't have to screw with that anymore. So that's going to stay the same thing. So that means when you calculate I, you just get the identity from the constants and something extra, but the something extra is going to happen at energy bigger than 0. And so we just have this abstract form here, which we then claim algebra tells me I can invert. So the calculation, really nothing deep happens. All that you need to know is that somehow any specific knowledge you have about your solution spaces, like for example they are empty, survives in the regularization. So that's sort of one master feature of regularization that we'd like. So, all right, and that means next time, really, I just need to prove to you, well, I need to fill in the black boxes and explain how to get algebraic identities in the black box speech.